Hello friends, warm welcome in this video that is the first part of Michaelis Menten equation. Friends, we have divided the videos on Michaelis Menten equation in three parts. In first part we will going to study the Henri and Michaelis Menten equation. In second part we will study the hardness modification of Michaelis Menten equation, and in third part we will study the significance of Michaelis Menten equation. So friends, as we have discussed in earlier videos, experimental evidences we showed that for many single substrate and pseudo single substrate enzyme catalyzed reactions, there was hyperbolic relationship between initial velocity V0 and substrate concentration S0. The equation for such graph V0 is equal to A into concentration of substrate divided by concentration of substrate plus B, where A and B are the constant. The constant A represents the maximum value of V0, it's called as Vmax, and B is the value of concentration of S0, where V0 is half Vmax. So from this equation, if we put the value of A as Vmax, then the equation will become V0 is equal to Vmax into S0 divided by H0 plus B, where Vmax is the maximum V0 at a particular enzyme concentration and B is another constant. In this case, the concentration E0 indicates the total concentration of enzyme, that is the enzymes which are free in state as well as the enzymes which are bound to the substrates. Kinetic models to explain these findings were proposed by Victor Henri in 1903 and by Leonor Michaelis and Maudy Menten in 1913. These are essentially similar, but Michaelis and Menten did great deal of experimental works to give their treatment a sounder basis. Therefore, unlike Henri, they recognized the importance of using initial velocity V0 rather than any velocity V. So let us consider a single substrate enzyme catalyzed reaction where there is just one substrate binding site per enzyme. The simple general equation for such a reaction would be E plus S will convert into ES with a rate constant K1, which again converts into E plus P with a rate constant K2. Once E plus S get converted into ES, it may again release the substrate and may convert into enzyme plus substrate, or the ES complex may convert into enzyme plus product. In some reversible reaction, the enzyme plus product may also again convert into the ES, which again give the enzyme plus reactant. So this is the simplest general equation for such a reaction. If investigations are restricted to the initial period of the reaction, the product concentration is negligible and the formation of ES from product can be ignored. Under these conditions, therefore, the reaction simplified still further as E plus S, which converts into ES with a rate constant K1, and then ES can convert into E plus P with a rate constant K2, or it may break down into E plus S with a rate constant K1. Here in this case, in the initial period, the concentration of product is very less, and that's why at a low concentration, the conversion of product into ES is negligible. That's why here we have not used the rate constant K minus 2. The rate of formation of ES at any time t within the initial period when the product concentration is negligible is equal to K1 concentration of E into concentration of S, where E is the concentration of free enzyme and S is the concentration of substrate at a time. Also at a time t, the rate of breakdown of ES back to E and S is equal to K minus 1 into concentration of ES, where ES is the concentration of enzyme substrate complex at this time. The Michaelis Menten assumption was that an equilibrium between enzyme substrate and enzyme substrate complex was almost instantly set up and maintain the breakdown of enzyme substrate complex to products being too slow to disturb this equilibrium. Using this assumption, therefore, K1 into concentration of E into concentration of S is equal to K minus 1 into concentration of ES. These constants may be then separated from the variables which gives concentration of E into concentration of S divided by concentration of ES is equal to K minus 1 divided by K1, which is equal to Ks. Here Ks is the dissociation constant of ES. The total concentration of enzyme present, that is E0, must be the sum of the concentration of free enzyme, that is the concentration of enzyme, that is the concentration of free enzyme, and the concentration of bound enzyme. Therefore, in order to involve total enzyme concentration, a quantity which can easily be determined and specified into the above equation, the following substitution can be made. So the concentration of free enzyme is equal to concentration of total enzyme E0 minus concentration of enzyme substrate complex. So if we put the value of E into this equation, then it will be look like this: concentration of E0 minus concentration of ES into concentration of S divided by concentration of ES, which is equal to Ks. Now if we rearrange this equation, that is taking this ES to the Ks side, then the equation will become Ks into concentration of ES is equal to concentration of E0 minus, in bracket, concentration of E0 minus ES bracket close into concentration of ES. After solving this equation, it will become concentration of E0 into concentration of ES minus concentration of ES into concentration of ES. So now we can take commons from this equation. Here the common things are concentration of ES, which are present in these two equations, that is Ks concentration of ES and ES concentration of ES. So if we rearrange this equation, then it will become concentration of ES into concentration of ES plus Ks into concentration of ES, which is equal to concentration of total enzyme E0 into concentration of ES. If we take the common ES outside the bracket, then the equation will become concentration of ES in bracket concentration of S plus Ks bracket close, which is equal to concentration of total enzyme E0 into concentration of ES. Here we have only taken ES as a common and taken it out of the bracket. So if we rearrange this equation, that means if we put this value at this side, then equation will become concentration of ES is equal to E0 into concentration of S divided by, in bracket, concentration of substrate plus Ks bracket close. ES has been included in this way because, as we have discussed earlier, this term governs the rate of formation of product. The overall rate of reaction according to the relationship V0 is equal to K2 into ES. If we substitute the expression for ES derived earlier, that is this equation, in this equation, then we will get V0 is equal to K2 into concentration of E0 into concentration of S divided by concentration of S plus Ks. Moreover, we know that when the substrate concentration is very high, all the enzyme is present as the enzyme substrate complex and the limiting initial velocity Vmax is reached. Under this condition, Vmax is equal to K2 into concentration of E0. Therefore, we substitute Vmax for K2 E0 and the expression for V0 will convert into V0 is equal to Vmax into concentration of S divided by concentration of S plus Ks. It was further assumed by Michaelis and Menten that the substrate was usually present in much greater concentration than the enzyme. This is generally true for enzymes, like all catalysts are often present at a very low concentration. It is important to realize that we can talk about this substrate concentration being low and giving first order kinetics with a very small degree of saturation of the enzyme, while at the same time the substrate concentration may be 1000 times that of the enzyme. This is valid because the formation of the enzyme substrate complex from the enzyme and substrate is a reversible process. If we make the assumption that the initial substrate concentration S0 is very much greater than the initial enzyme concentration E0, then the formation of the enzyme substrate complex will result in insignificant change in a free substrate concentration. Hence the expression for V0 derived above, we can substitute S0 for S. This is an equation of the form required to explain the experimental findings. However, it is unsatisfactory in that the Michaelis-Menten equilibrium assumption cannot be generally applicable. Some possibly many enzyme catalyzed reactions are likely to proceed at rates fast enough to disturb such an equilibrium. Thank you.